Well, hi everyone. I'm Colleen Boss with CTC and Associates, and I want to welcome everyone to the final presentation webinar for the Clear Roads project to develop a best practices manual for the prevention of corrosion on DOT equipment. And I would like to welcome Laura Fay from the Western Transportation Institute. She's been fulfilling the role of PI on this project and will be presenting to us today. Before I get started, I also want to thank my colleague Greg Wadley, who's helping out behind the scenes with this webinar. We are recording this webinar and planning to post it, so it'll be available on the Clear Roads website and our YouTube channel. So anyone who had to miss today's presentation will get a second chance to see it. Without further ado, I'm going to turn this presentation over to Laura Fay. She is requesting that you hold questions till the end unless you really think there's a chance you're going to forget to ask something important. Laura, go ahead.
Great. Thank you, Colleen, and thank you everybody for calling in to participate. As Colleen mentioned, I've taken over as PI for this project, and the bulk of the content was developed by Sean-Ming Shi, Dr. Mehdi Nazari, and Mr. Dave Wagner. So if you do have questions at the end, they have been invited to participate, and I would encourage you to direct questions even directly to Sean-Ming if they're specific to the content. So without further ado, this is the presentation of the Manual of Best Practices for the Prevention of Corrosion on Vehicles and Equipment used by transportation agencies for snow and ice control. And I'm just going to quickly mention, if for some reason you cannot view the go-to webinar page, I'm using the PowerPoint that is in the final report. So you can open that PDF document and also follow along that way. All right, so quickly, this presentation includes an introduction to corrosion, defines various types of corrosion that are commonly seen on DOT vehicles, the causes and effects of corrosion, materials commonly used for snow and ice control, and new equipment specifications, repair and rehabilitation and retrofitting of existing equipment to handle corrosion, preventative maintenance and practices for equipment, training and facility management, and then provide some nice conclusions to summarize what's presented in the document. An introduction to the topic. Let's see. Large amounts of de-icers are applied onto winter roadways. De-icers used by highway agencies are commonly chloride-based, and these are your sodium chlorides, mag chlorides, and calcium chlorides. These corrosive salts are a major risk to DOT vehicles, and overall the benefit-cost ratio for further improving corrosion from de-icers to DOT fleet equipment has been estimated to be about 13.2. And here you can see two pictures of some jump body corrosion and then corrosion at the spreader controller for de-icer application. So getting into corrosion definitions, corrosion is the deterioration of material due to the reaction with the environment. Carbon steel, cast iron, aluminum alloys, magnesium alloys, copper, and copper alloys, which are used in different components of winter maintenance vehicles, can be corroded by de-icers. And a variety of corrosion forms can take place in a vehicle, which can be divided into these specific groups that we'll present. General corrosion is when the surface area deteriorates at the same rate due to poor material selection, and you can see that in the two pictures provided above. General corrosion can be included in design calculations, such as increasing the wall thickness of the metal, and it's easy to prevent by good material selection using coatings and corrosion inhibitors. Localized corrosion occurs in confined areas of a space, whereas the other parts of the surface experience a much lower corrosion rate. Localized corrosion can cause unexpected failures of equipment, and localized corrosion can be divided into many subclasses, including pitting, filiform, intergranular, galvanic, SCC, fatigue, fretting, and crevice, which I'll discuss right now. Pitting corrosion is a severe form of localized corrosion in which damage in the shape of deep holes occurs, and off to the right is a photo of pitting corrosion. Crevice corrosion occurs at the interface of a metal in another surface, often where a small volume of stagnant solution is contained. And you can observe that in the picture of the two screws on the right. And filiform corrosion is a special form of crevice corrosion, which happens beneath some types of coatings and can be observed in the photo to the right, circled in the red oval. Intergranular corrosion occurs at grain boundaries. Specifically for stainless steel, this occurs in heat-affected zones, a short distance from the weld. Galvanic corrosion occurs when two dissimilar metals are in contact, where the less resistant metal corrodes much more than the more resistant metal, which corrodes very little or not at all. And again, you can see pictures of these on the right-hand side of the slide. Stress corrosion cracking, or SCC corrosion, is the damage caused by the interaction of mechanical stress and corrosion. Corrosion fatigue is a special kind of SCC corrosion caused by the combined effects of cyclic stress and corrosion. Rust jacking is a kind of corrosion fatigue and is the displacement of building elements due to the expansion of corrosion products. And this is best shown in the picture on the far right, where you can see the little kind of reddish-brown pieces of rust pushing up on the metal. Fretting corrosion happens at the interface between contacting loaded metal surfaces in the presence of slight vibratory motion. All right, so let's get into the cause and effects of corrosion. Chloride deicers are easily available, relatively inexpensive, and easier to use for winter maintenance than non-chloride deicers, despite their higher risk to vehicles and equipment. The average estimated annual cost per agency for corrosion management are listed below for training programs, material selection, design improvements, corrosion monitoring and testing, and proactive and reactive maintenance. And as you can see from the list below, reactive maintenance and material selection have the greatest budgets. Corrosion-prone parts. Here's a pie chart showing corrosion-prone parts. And the most severe corrosion-prone parts include electrical wiring, frames, brackets and supports, brake air cams, and spreader shoes. And high repair costs are associated with the chassis, axle, brakes, frame, suspension, tire and wheels, and electrical components. Cost-benefit analysis of mitigating deicer corrosion to DOT equipment has been done, but generally limited data has led to the need for just estimations, and that's what we'll present here. So for an average agency, it's assumed that the empirical 20 or 80-20 rule may apply to 25% of corrosion costs, which can be avoided by best practices, and the absence of actual data being available. So in other words, you can reduce the current cost of corrosion risk related to deicer exposure by 80%, multiplied by the 25% of corrosion costs, if the agency can increase its current investment in corrosion control by 20%. This is possible by conducting risk analysis to identify the critical 20% of corrosion-related failures and focusing more on training and risk maintenance. Based on the data from the survey responses, the cost-benefit ratio for further improving corrosion from deicers to DOT fleet equipment can be estimated to be approximately 13.2. Materials used for snow and ice control. Generally, the materials used for snow and ice control are either chemically inert or active. The chemically inert materials have no de-icing properties. They simply provide traction on icy pavement surfaces. So we're talking about sand and abrasives here. The chemically active de-icing materials commonly include sodium chloride, calcium chloride, magnesium chloride, potassium acetate, calcium magnesium acetate, sodium acetate, and potassium formate. So new equipment specifications. So this is built to last. Is it worth the cost? Of course it is. Many of the design and construction recommendations may add to the overall cost of purchasing a new equipment in the range of 10 to 20%, over an agency's current specs. However, this increase in capital equipment outlay is justified by the long-term reduction in maintenance, and this includes repair, replacement, and reconditioning, all due to corrosion. And what we'll talk about now are metal material selection, design improvements, considerations for welding joints, and coating for corrosion protection. Metal material selection. Metal alloys and mill product forms of aluminum alloys in these various categories should not be used for structural applications. The use of the 7 series of the aluminum alloys should be limited to a thickness of no more than 0.08 inches. Where stress corrosion cracking is a main problem, the 7075-T6 aluminum alloys can be replaced by the 7050-T7451. Higher carbon content and hardness in steel can make it susceptible to the stress corrosion cracking or embrittlement. In SCC of stainless steels in the 300 series, bichloride substitution with the duplex stainless steel will often eliminate this problem. Using steels containing molybdenum, such as stainless steel 316, can reduce pitting corrosion. And intergranular corrosion can be reduced by using the stabilized 321 or 347 or the low carbon stainless steels. Design improvements. Where water may accumulate, include holes for drainage, and the minimum diameter for all drain holes should be 9.52 millimeters, or about 0.375 inches. The drainage holes should be shielded or oriented to avoid direct road splash. Avoid sharp corners that make it difficult for protective coatings to function, and remove notches and other stress concentrating features. Rounded fillets and angles also reduce stress concentrations. Crevice corrosion can be minimized by proper design of welded joints and gaskets that minimize crevices, and sealing the crevices and as well as using periodic cleaning. Contact between dissimilar metals should be avoided. Where it is not possible, both metals should be coated. Using a coating with low water vapor transmission characteristics is and excellent adhesion. Zinc-rich coatings can be considered for carbon steel because of their cathodic protection ability. So considerations for welded joints. On the right, there's a figure of do's and don'ts that's provided in the manual, and I'll quickly discuss what the figure shows. So eliminate the weld splatter using blasting or chipping. Rough welding should be ground smooth. If feasible, welds should be double coated. Where corrosion is possible, use continuous welds instead of discontinuous welds, like tacks or skip welds. Remove brackets and extra metal, followed by grinding smooth areas of previous contact. And remove weld flux after finishing the weld. So protecting your asset by professional coatings. Here's 3 examples that you can see in the slide. You have a trailer on the left, on the top left, that was previously rusted with chipped paint. It was sandblasted clean, shown in the middle photo. And on the top right, you can see the camo painted trailer that is now protected from corrosion. On the bottom left, in the photos labeled A and B, you can see a piece of equipment that has rusting all around it. And the piece of equipment shown in the photo B has been sandblasted and repainted. Repair, rehabilitation, and retrofitting of existing equipment. So the evaluation process for fleet, a thorough inspection and operational check for each unit should be conducted, and an initial itemized list of repair and maintenance work for each vehicle should be completed. A general assessment rating using a standardized grading such as alphanumeric or a defined term is a great way to do this. And a priority ranking for each item, for example, critical, urgent, needed, or recommended, is one way to show corrosion issues that need to be handled. A detailed cost estimate for each vehicle, a determination of expected service life if repairs or rehab is done, a decision for the course of action for each unit of equipment, and then the final cost estimate based on this evaluation should be completed. And ultimately, the repair and restoration. And on the right-hand side, you can see this piece of equipment that had some repair done and what it looked like on the right-hand side. So in this case, restoration means replacing a full component. And then modifications, such as replacing strobe warning lights mounted on the cab of a roof with ones mounted on the crossbar, will not only replace maybe some corroded equipment, but also reduce corrosion in the future by not having holes drilled in the cab roof. Protecting equipment assets by preventative maintenance. And this slide shows a couple examples of preventative maintenance that was done to reduce corrosion. So two primary ways to deal with corrosion are reactive and preventative corrosion prevention. Reactive methods are used to deal with existing corrosion by cleaning corroded parts with a rust-removing compound or replacing the ones that are too far gone for rehabilitation. A reactive treatment may in some cases be the most effective means of dealing with corrosion if the parts are easy to clean or easily replaced and fairly inexpensive. Preventative methods are the proactive strategies which may involve the use of corrosion-resistant materials for equipment components, dielectric grease, enclosed wiring connections, the use of sacrificial anodes, the use of coatings, the use of corrosion-inhibited products, and frequent and regular washing of equipment. So here's a great photo of some wash bays that are being used. And the slide says, wash your vehicles daily. And I know that not everyone can do this, but it's a recommendation that we feel will greatly reduce corrosion rates. So let's get into the specifics of washing to prevent corrosion. Washing should be concentrated on trouble spots like frame rails, brake components, underneath the chassis, and other areas that tend to collect material. Perform routine washing, preferably with hot water, and then fast drying. Preferably, do not use a pressure washer because water can be forced into areas that cannot escape, and this can lead to further corrosion. Instead, use low pressure wash with a high volume or flow rate of about 300 psi or gallons per minute. Use physical action together with washing to remove road salt, and use salt removers or neutralizers to remove the salt captured in crevices. The effectiveness of salt neutralizers is alloy specific, so please make sure you're using the appropriate salt neutralizer for the type of metals you have on your vehicle. More cleaning liquid is not always better. A high concentration of washing compounds may attack some of the plastic components on a vehicle. And once active corrosion of metals has started, washing should be coupled with other means, such as applying a spray-on corrosion inhibitor. Electrical issues. Eliminate the junction boxes wherever possible and relocate them inside the cab off the floor. Install modified protective cover for batteries. Use high-quality weatherproof terminations such as bus-style connectors and compression fittings, in addition to shrink-wrapping susceptible electrical wiring components. Do not probe the wires to test for continuity, and avoid any damage of wiring insulation. Apply non-conductive, non-sodium-based dielectric grease on all electrical components. Clean the electrical connections on a regular basis, at least every 6 months, with water, not soap, and a wire brush, and then re-grease them with the dielectric grease. Minimize connections or connectors to the extent possible by using continuous wiring and use anti-corrosive spray for protecting the battery posts and terminals. Do not apply paint to the rubber seals around lights. Brake components in the chassis. Inspect all brake components, even by removing brake drums, to check the entire lining surface and the brake shoe web, rollers, and cams. Be careful about automatic slack adjusters, or the ASA, and make sure the ASAs are thoroughly lubed and do not show evidence of internal rusting. Be careful about automatic slack adjusters, or ASAs. Make sure ASAs are thoroughly lubed and there is no evidence of internal rusting. Require throttle, brake, and clutch pedals to be suspended in specifications. Install corrosion-sealed brake chambers and a spray-on protective coating on all brake valves. Pull brake drums on a regular basis. Use rubberized undercoatings for aluminum brake valves. In the rebuilding process, specify rust-proof painted and epoxy-coated brake shoes. Specify self-healing undercoats, full fenders, and fender liners for the chassis. And install a large, full-width, full-height under-chassis sand guard on all front discharge sanding bodies. For the frame, body, bed, and other parts, carbon steel, fuel, hydraulic, and air tanks can be replaced with aluminum tanks. Replace standard E-coat steel-painted wheels with powder-coated versions. Use powder coating for fuel tank and frame rails. Use stainless steel truck boxes, Use stainless steel truck boxes, pre-wetted tanks, and sanders. Use zinc anodes in solution tanks and zinc nickel alloy engine oil pans. Use stainless steel couplers under tailgate spreaders and cooler. Use polyface snow plows to reduce corrosion and also lessen the weight. Use greasable tailgate linkages and attach them to onboard automatic loop systems. Replace radiators every 2 years. Install grit guards on wheels. Wrap hydraulic fittings with anti-corrosive wrap. And use glad hand seals with dust flaps for the air system. This slide shows an example of in-field success of some proactive maintenance methods. The photo A in the top left is the aluminum fuel tank. The picture on the top right, or B, is a stainless steel hydraulic pipe. Photo C on the bottom left is the poly-tandem fender guards. And photo on the bottom right, photo D, is the E-coated frame rail. So training and facility management to reduce corrosion. Operators, including contractors, need to know the basic characteristics of each product being used, including inert abrasives. Mechanics who repair and maintain the fleet need basic information on the materials used and the associated characteristics, especially an understanding of the corrosiveness of each chemical. Supervisors and managers are responsible for making sure that operators and mechanics and others involved in the transporting, handling, and storing of materials have proper training. Good housekeeping should be an everyday standard at any agency facility where materials are stored and handled. Accelerated durability tests by the U.S. Army. So this shows a diagram of the testing program that they had. So on the left, you see the testing condition, and they tested on gravel roads, rolling hill courses, a high-speed track, and then a frame twister. And what they saw was that the gravel roads caused damage to the coating. The rolling hill course exposed the vehicle to twists and turns. The high-speed track simulates the high-speed travel and introduces high-frequency vibrations. And the frame twister promotes initiation of corrosion in stressed joints and seams. And based on the test, they accurately simulate about 10 years of cosmetic corrosion and about 3 years of crevice corrosion. So to bring this all together and summarize what this manual states, agencies should track the data relevant to analyzing the direct costs of de-icer corrosion to their equipment assets and the direct benefits of countermeasures to enable reliable, quantitative cost-benefit analysis. Agencies should implement an extensive preventative maintenance program that may involve use of salt removers or salt neutralizers, together with routine washing, protecting of electrical components by sealing or moving them inside the cab, reapplication of post-assembly coatings, spray-on corrosion inhibitors, and many other operational changes which can be supplemented by corrective maintenance practices to minimize the negative impact of corrosion from de-icers to equipment assets. Supervisors are responsible for ensuring compliance with procedures and practices regarding vehicle inspection and operation, and also staff and contractor training. And just to finish this all up, I'd like to acknowledge the Clear Roads Technical Advisory Committee, Colleen Boss for her assistance and management of the project, Scott Jungworth, Carla Little, Dana May, Sean Ming, Mehdi, Dave Bergner, and then a lot of the DOTs that helped us by providing photos and information. So with that, I will open it up for questions.
Yes, hi, this is Scott Lucas with Ohio. I was just kind of curious. I know she had about the de-icer and washing, or not de-icer, I'm sorry, salt neutralizers and that. Did you make any determination which salt neutralizer worked best or anything like that as well?
What I'll direct you to is actually there's a section with more detail on that in the manual that does talk about some specific products. But as mentioned in the presentation, they are specific to different metal types. And so just be wary of what product you're using and what metal type you have on your vehicle or your equipment.
Okay, thank you very much.
This is Clay Adams from Kansas. On the slide pertaining to truck washing, you indicated a low pressure, high volume was preferred, 300 PSI and 300 gallons per minute. I wasn't sure if that 300 gallons per minute was a typo or if that just sounds like an awfully lot of water.
I would need to go back and check in the main body of the manual to see if that's a typo or not. Sean Ming, there were a few questions that maybe if you're on the line you could respond to regarding specific types of salt neutralizers.
Sure. Sorry, I somehow dropped out, so I dialed in again. What was the question?
It was with regard to specific types of salt neutralizers.
Mm-hmm. Can you be more specific?
This is Scott Lucas, Ohio. I was just curious, what type of salt neutralizers did you test? And did you determine if one was better than the other or more usable on that?
I think the overall this project was just to synthesize information, trying to make it more usable in a manual format. So much of the information was based on our phase 1 study, which was funded by Washington State DOT. And in that, the salt neutralizer test was really a small, tiny portion. So it was more like a 2-week test. So it's not supposed to realistically simulate what's happening in the field. So I have to say the disclaimer. In that case, there was a paper published and also a report. Cannot remember the top of my head, but there were 2 products which showed some promise. I think wasn't one of them hold tight. I have to go back. But in general, the 4 or 5 products we tested all showed benefits. It's just, one of them showed the most benefit in terms of mitigating corrosion by magnesium chloride. Again, my concern is taking any of those findings and dump it into the user manual is a little risky because there's no field testing. Because of the nature of the phase 1, also the nature of this project, basically there's a gap in between. We don't have any sort of field validation whether the findings from lab study would really stand over the long term in the field environment. So lab studies are just lab studies. So it's hard to make a solid recommendation based on a 2-week test. Yes.
Okay, thank you.
Oh, I hope that sort of, yeah, we can certainly, follow up after this call. But yeah, basically right now there's no field testing. But I know Ohio funded a study to look at salt removers. That was kind of, the time was about a little bit later than the Washington DOT project, a little bit earlier than this project. So we did try to incorporate the findings into this manual, I believe.
All right. And Clay Adams, I was able to find on page 64 of the manual the recommendations in the washing section. And it doesn't appear to be a typo. It does say use low pressure wash and high volume flow rate of about 300 psi or 300 gallons per minute. And this is based on work by Clonch, published in 2014. So that's where the recommendation came from.
Okay, thank you. That's just contrary to whatever car wash that we have in Kansas, because we're pretty much high pressure, low volume. But that's
any other questions?
This is Tim Peters. I had one. On one of your slides it says once active corrosion of metals has started, washing should be coupled with other means, i.e. applying spray-on corrosion inhibitor. What does that really mean in practice? Does that mean we shouldn't be using salt neutralizer on a truck when we wash it once it starts notably rusting? Or
Sean-Ming, I'll let you handle this one.
Sure. Again, this is based on domain knowledge, not so much on the real testing. Unfortunately, we never had the opportunity to do field tests. But in general, there's some problem statement floating around, potentially trying to gather support by NCHRP and others. Basically, what we're trying to promote is, okay, the correct or the optimum procedure should be you have the washing process, and certainly you can play with the pH of the water and the pressure, the volume and all that, flow rate and stuff. And also, salt neutralizer certainly would be beneficial in terms of removing, again, well, actually, salt neutralizer is not the right term. It should be more like salt remover because they don't neutralize anything. What they do is really try to help better removal of residual salt out of crevices and places hard to get to. And then afterwards, unfortunately, if the corrosion is kind of active, you still need some protection. So that's where afterwards, if it's dried out and then maybe there's a need to apply some sort of protection. But I don't think any agency is doing that right now. Even salt removers, not every agency is doing that. Not to mention, afterwards, subsequently, application of corrosion inhibitors. But that's how it should be done. Of course, there's some concern about even the washing process. If it takes too much water, then the wastewater treatment, and also we even try to toss the idea around about washing it 2 steps instead of 1 step, because there's some type of salt remover which is more really effective, but basically they're acidic, so they're going to help you remove the salt, but if you leave them in there, it will actually be more corrosive. So you basically need another washing process to get rid of that. Unfortunately, many of these products are, proprietary, so they don't share with you exactly what the working mechanism is. So you basically need a third-party evaluation.
This is Ron. A lot of these salt washers that I've looked at in Idaho are typically made up of some kind of an acid compound, or, such as an acetic acid, isopropyl alcohol, sulfamic acid type rinse that's being placed onto it. And we've been playing with it for a couple of years in one of the districts. They like to use it, but I don't know if we've got data hang on the hat yet. But anyway, these things do have mild organic acids in them a lot of times, and that's why Laura's earlier point about being careful, don't to over-concentrate them, and to see what they actually pull out. One does have to be a little careful about where they're at and what they're contacting.
Thanks, Ron. Is there any chance you guys are going to put out any publications on your experience with those?
Not that I'm aware of yet.
Okay.
I would say it's only one place in one district that's utilizing it. Our biggest problem that we get, like so many other people, is that when your trucks do get caked up, it's so cold, it's hard to get them washed and cleaned.
Mm-hmm.
Having an active car wash, when you're in winter weather that you've had active snow and then all of a sudden it drops to, 0 or less for a month, it's really hard to get in and get them cleaned without just totally icing up the works.
Well, actually, I found this piece of information to answer the earlier question. Basically, the 2 products seem to stand out were Corrosion and Hold Tight. Again, with the disclaimer, they were just tested for 2 weeks, and mostly we dealt with 30% magnesium chloride and then diluted magnesium chloride solutions. So we were so worried about the mag because the sodium is much easier to remove. And yeah. I'm reading this paragraph in a paper we actually did not publish. But anyway, it's about future work should focus on the possible approach of using an acidic salt remover such as Corrosion, followed by the use of an alkaline salt remover such as Hold Tight. The use of first salt remover would effectively facilitate disbanding of residual chlorides from the metal surface and crevices, where the use of the second one would produce a hydroxide layer on the chloride-free surface and provide temporary protection against flash rust. In general, frequent washing of the equipment is recommended to minimize the possibility of chloride penetration into the metal surface, crevices, or coatings. Here, of course, we didn't mention the, coupling this washing process with subsequent application of corrosion inhibitor, but that could be another approach. But again, all these are just conceptual because there's no testing on them. And this, just to clarify, this ClearRoads project was intended to be a manual, just translating existing findings into something more user-friendly. So it didn't really involve much, well, any testing at all.
I know that working with the Steel Structure Paint Council, SSPC, that Corrosion has been used for, I know I've been using it for over 10 years or better as a chloride reducing agent to put on steel bridges prior to painting. And I believe that, different people within SSPC have done research studies on the amount of chloride that is reduced out of it prior to blasting off steel. because to us it's all about whenever you use a salt reducer in a wash spray to get salt down, you want to do that prior to doing any kind of surface treatment like blasting, which would peen the steel over and entrap the salt crystal and thus cause an early paint failure. And so we've used Corrosion for a number of years. There's been several research studies done there. I'm sure Corrosion, gentleman there by the name of Hap Peters, could provide lots of information that they've done or what other states have done with their salt neutralizer.
Right. They actually gave me the information. The challenge there is it's all sponsored by them or conducted by them. So
well, and that's what I'm saying. There is stuff that was done through SSPC, and I think one of the research labs that was out there was KTA Tater. That did some work on it, and I think there was another outfit that did some analysis work.
Yeah, there's an ongoing, there's a new NCHRP project which just got funded, or it's underway right now.
Yeah.
Looking at this issue, cleaning basically steel bridge surfaces before doing any sort of coating, so that because the residuals out there is a major problem. If the coating, if it's not clean surface, the coating won't last very long.
And there is mechanisms out there. I know that Corrosion sells a field kit, and I buy these things religiously. They're very easy to use, and you can monitor what the salt concentration is on the steel prior to painting it or after washing it. So you could run one prior to and then run one after, and it gets you pretty good numbers relatively very quickly.
All right, any other questions or comments?
I seen one on one of your slides earlier when you were talking about, I can't remember exactly where it was. It was something about having something on the snowplow that was plastic, and then there was, like right after that, it said stainless steel.
Oh, that was.
I didn't know if it was an add-on of trying to look at using stainless steel plow blades.
Again, I'm going to hand this over to Sean Meng to address that specific comment. It's under frame defect.
Oh, this one?
Recommendation is use polyphase snowplows to reduce corrosion, and they also reduce weight, or use stainless steel.
Oh, no, there are two different options. Basically, not so much about the abrasion issue, it's more about the corrosion issue. Basically, it's just, I think some survey responses we gathered from the previous study, funded by Washington, there we run almost an international survey. So basically people's experience is try to use more corrosion resistant materials in general for corrosion prone parts. I think that's what.
Got it. That was about the time I lost audio, so I was kind of trying to back up. Thank you.
Sure. But again,
while you're on that slide, I have another question. One of your bullet points, the fourth one up from the bottom, replace radiators every 2 years. Is that based on Washington's experience or someplace that's using a lot of mag, or where does that come from?
That's a very good question. Yeah, it was from Washington. I think this every 2 years could vary, that frequency depending on where you are or how severe the situation is. But that was Washington's experience, where they use a lot of mag, of course. Again, many of these recommendations are anecdotal, from practitioner experience, so they're not really, field tested or, scientifically sound, I guess. So when you transfer that knowledge, you need to look at your local experience.
This is Scott again from Ohio. I know one thing, I know Clay was asking about the whole pressure and volume calculation. And I was thinking actually like 30 PSI around 300 PSI for low pressure, but I know that's one thing we've had a situation here at ODOT that we went back and forth on how to wash the vehicles, and the reason for the high volume was and low pressure was to try not to introduce salt and other materials inside electrical systems. And that guys were actually power washing so hard they would pierce the covering of the electrical wiring, and it would introduce salt into the wiring and start rusting the harnesses out. So that's the reason we kind of went the other way. Because I definitely agree with what Clay said. It's totally opposite what a lot of your car washes do. But it also, though, being that low pressure and high volume, also creates more of a wastewater issue that you have to deal with. Then you don't have a economical way of treating wastewater.
Yeah, I think the source, Laura mentioned, was probably from Diana Clunch. She used to work for Ohio DOT, and she probably got the information from other sources. So it's kind of convoluted.
All right, any other questions or comments?
I guess I'd be interested, going back on this car washing, I'd be interested in, and I may send an email out just to see if there are any states that are using low pressure, high volume washing systems for their snow and ice trucks or just their maintenance equipment in general.
You know, Clay, Lisa Kunzman, who's working for Caltrans, she's also the current chair for TRB Committee on Maintenance Equipment. I forgot the exact name of the committee, but anyway, right. She's doing some follow-up work. Maybe you want to touch base with her.
Okay.
Clay, I agree with you, because washing these vehicles at 300, gallons per minute, if you wash it for 4 minutes, that's 1,200 gallons, and that will fill up your holding tanks very quick. A lot of our sites are not even on solar connection, that you have to remove that water and throw it away.
Yeah, that's been, Gabe, that's been a real big problem, like I said, in Ohio too. We have 2 different schools and all that stuff, because then we had to start looking at ways of taking wash water, which is classified as industrial wastewater, but then also do a project to try to convert that into brine. And even at that rate, you're still way over. I mean, we start thinking of washing the trucks and everything like that. It creates a lot of other issues. So it's a headache, to say the least.
Yeah, Virginia has done some work on that, basically turning it back into brine, but they basically have a detention pond or something like that. It's a big operation.
Even if I don't think our DEP or EPA will allow us to put in a detention pond, because to have that, salt and have some of the chemicals from the washing material.
While you're on this slide, can you go over the use zinc anodes in solution tanks and zinc nickel alloy engine oil pan? I'm not sure I understand this zinc anodes in solution tanks.
I think, based on my understanding, that's something Oregon DOT had played with, and their preliminary investigation shows some promise, I guess. It's basically they're trying. Well, typically, in my opinion, it would be probably easier to just use a zinc-rich coating. So basically, what it does is the zinc will sacrifice itself to protect the underlying substrate, say if it's a steel. But in their case, because there's the acid solution tanks has so much corrosion, they try to, because they think the zinc-rich coating is not fast enough, so they actually distribute zinc anodes, and it seemed to work. But we can certainly follow up with Oregon to get more details. They have some detailed configuration, how they did it exactly. And the other one, the zinc nickel anode engine oil pan, I think it's just a material selection issue. They select this type of anode so that it's, again, the zinc basically serves as a sacrificial anode to protect the metal itself. So it's kind of like galvanized steel in a way. It's just a material selection. But the first half, I mean, the zinc anode is really something you mount onto the tank, which is a very unusual practice. Probably Oregon is the only agency has done it.
Yeah, I think there's another research project going on. I can't remember if it is a TRB or an NCHRP research project that's very similar to this project, but it was more specifically about the use of anodes to reduce corrosion, and so it may be addressed there. I can remember.
So maybe you're referring to that problem statement Lisa Kanzman is trying to get funded by NCHRP. I'm not even sure whether it will be funded or not. But it did come from the Oregon experience. I mean, I think, was it Greg from Oregon is the champion behind it.
Okay.
The state equipment engineer.
Are there additional questions?
Laura, just one little comment from me is I would feel more comfortable not classifying corrosion fatigue as a type of SCC, even though they're both dealing with stress. Probably keep them separate. Somehow I did not catch that earlier. Basically, corrosion fatigue is more dealing with cyclic stress, and SCC is more dealing with tensile stress. So I would not call corrosion fatigue as one type of SCC, but that's really how you classify it.
Okay, I have a note to do that.
And also for other folks who are still on the line, basically there are two problem statements floating around. I don't know what Lisa has done to it, but one is related to the zinc anode and zinc-rich coating issue or solution, and the other one was more related to the washing. So if you're interested, you can contact Lisa to find out what's going on, because I don't know exactly the status of those. And if you have questions related to this report, I mean technical questions, feel free to contact me, I guess.
I do have one more quick question, Xiaoming. On the slide that's up, it says install grit guards on wheels. What is a grit guard?
Well, the short answer is I don't know where this came from. Some server response, we can go back and look. My gut feeling is it's really just the grit guard is really probably preventing the abrasion of the wheel by the abrasives, I guess. But anyway, we can look back who provided that comment.
All right. Colleen, if there's no other comments or questions, do you want to close this out, or should we?
I'll close this out. Just one more reminder to folks to get in your comments and feedback by the end of the day, Thursday. I'll send you a reminder on that. And thank you, Laura, and thank you to everyone who participated. I really appreciate it.